Hello and welcome to this video where I'm going to explore some of the really small topics or things that come up in the pure papers that students often forget. And they're really all within your curriculum. There's nothing new in the sort of what I'm going through here. Some of these things I'll talk through, some of these things I'll sort of uh, you know use my writing tab to explain as well. So let's go in no particular order. We'll just start from the top. Exponential dy dx for a to the x. So essentially, one of the things that is in your curriculum is the derivative of a to the x, an exponential function, which is an e. So you should know that y equals e to the x, that differentiates to itself, okay? But what about y equals a to the x? In that scenario, the results for this is as follows. A to the x ln a. So in an example, where could this be used? This could be used in many different examples with product rule questions or whatever with differentiation. It comes up now and again. So if I had to differentiate y equals 3 to the power of x, that result would be equal to 3 to the x ln 3. The proof of that is in your textbook as well, so it's well worth looking at. But again, one of those things that I think students forget or they're not really completely always sure on. The other thing that is really useful to remember is essentially when they apply uh, an integration of a trig function to a power, so something like sine squared or cos squared. Now, if you have a question which involves integrating something like this, you cannot integrate that directly. You have to integrate that indirectly. Okay? There is no direct integral of sine squared x or integral of cos squared x. Yeah. So what you've got to do is use something called the double angle formulas. And in particular, you're going to use the cos one. The cos 2x has three variants. Okay. There's cos squared x minus sine squared x. There's 1 minus 2 sine squared x. And there's 2 cos squared x minus 1. They're all equal to cos 2x. So if I wanted to integrate sine squared x, I would look at this in this identity, uh, and I would literally just make sine squared x a subject. Okay, so I'll put the 2 sine squared x on the left-hand side. Becomes 2 sine squared x, 1 minus cos 2x, and then divide by 2. So essentially, when you're integrating sine squared x dx, you're actually going to be integrating half 1 minus cos 2x. Okay, and you can do a similar sort of process for cos squared x. Okay, so you would go, okay, can I make cos squared x the subject with the cos 2x, and then you're going to have to rewrite that. So don't forget, you can't directly integrate sine squared x or cos squared x. You have to do a double angle formula there. So yeah, those two are now covered. What about derivatives of these? Well, when you've got, let's say, um, and sometimes this does come up, if I was asked to differentiate this, then a lot of students can sometimes panic or freeze. I mean, really, if you convert it into a sine x to the power of 2, this becomes a chain rule problem. Okay, so what's your inner function? How do you write that in terms of u? And you differentiate that. Okay, so that's the derivative there. And you can apply the same principle to cos squared x as well. So, gone through that. Now, another sort of key thing that comes up in the pure papers is around sequences and series. I've seen questions around this quite a few times. Uh, Things like they give you, let's say, if we have an arithmetic, okay, you've got an arithmetic sequence, I don't know, p plus 2, uh, 3p minus 1, something like that. And then they'll say to you, find the first term or something. And when you do arithmetic sequences, often you're looking for a common difference. And some students, they understand what common difference is. It's the difference between one term and the next. You're going either up in a number or going down a number. But I think something that is kind of implicit in that knowledge is really the common difference can be any term take away its previous. Okay. So any term take away its previous is basically the common ratio, but that can be applied across the whole sequence. So, for example, if I say u2 minus u1, that's equal to the common difference, d not r. And that's the same as U2 minus U3 minus U2. That will also give me the same common difference. So how can you use this knowledge in questions like this where you're given a sequence in arithmetic where you don't really know the numbers? Well, you'd say to yourself, okay, 3p minus 1 minus p plus 2 equals p plus 2 minus p. Okay, and that can solve to get you an unknown value of p. So when we have questions with unknowns and arithmetic sequences, just think, okay, common difference is the same if I just take away difference of terms, difference between terms, okay, and I can make them equal to each other. So that's one of those sort of things that it's quite implicit, but you need to know it. And the same applies for geometric, but in a slightly different way. So if I had a geometric sequence, in a geometric sequence, what you're doing, let's say, is, I've got something like this, k, I don't know, 2k squared, something like that, plus one. I'm literally making this up. 3k cubed minus three, I don't know. And again, you have to somehow deal with the geometric sequence and answer questions on it. Well, in geometric sequence, you need to know your common ratio. What are you multiplying by each to get the next term? And again, the common ratio, you can say that's equal to a term divided by its previous. And you can apply that across the sequence. You can say, okay, the third term divided by the second term, that's equal to the common ratio, which is also equal to the second term divided by the first term. Yeah, which is obviously you write it as A. So you can apply that in that way, and then you can solve to get unknowns. Okay. So those are one of the sort of well, the sort of the two sly ideas which come up in sequences and series. Other things that I think you guys need to be aware of, sum to infinity. So I think a lot of learners, they need to really understand this. Sum to infinity has strict conditions. You can only apply it on a geometric series. Yeah. And furthermore, you can only apply it when the common ratio in that series is between -1 and 1. Okay, not inclusive. Why? Because essentially what we've got here, if your R value is between -1 and 1, we have what we call a convergent sequence. A convergent sequence or convergent sum, sorry, means that the sum, if you add up all the numbers of that geometric series, which has a common ratio one minus between -1 and 1, if you're to add up that sum, it converges to a limit. Okay, so I'll show you an example here. Here's a series, 1/2, quarter, 1/8, 1/16, etc. This is this is a geometric series because I'm multiplying by half. It's convergent because if I start adding, I'm going to get 1.5, 1.75. If I start adding the first three times 1.75, add that in 1.875. Essentially, you'll see this is going to be like 1.9 something. You'll see that this will eventually approach a limit called 2. And that's what the sum to infinity gets you to. But you can only use it if it's the R values between -1 and 1. And some students forget that. So again, this is the formula, and I can use the formula to tell me that. So 1 minus a half, that is 2. That's the sum to infinity. Okay. But remember, if you see something in the exam, paper 1 or paper 2, convergent sequence, you have to link that with common ratio. Okay. So that's something there. Okay, so I've gone through these things here. Linux graph. I think students really, really forget the Linux graph. The Linux graph looks like this. Okay, the Linux graph looks like that. And generally, you should know it cuts at one on the x-axis. It doesn't touch the y-intercept and it doesn't become negative. Okay, but you could be asked transformation questions on that. And I'm actually going to link that with the next thing. How do I get Linux generally? Well, the Linux graph, the Linux function is actually the inverse of the exponential function. Okay, so it's the inverse of that. But how do you draw an inverse generally? To draw an inverse, what you do is you reflect a curve with a one-to-one mapping or a graph with a one-to-one mapping in the line y equals x. So if you ever asked in pure one or pure two across those two papers to draw the inverse graph, then you have to reflect it in the line y equals x. That's how you generally get the inverse. Okay, so I've tried to do two birds with one stone here. Remember Linux graph, and generally speaking, how do you get the inverse through sketching? Um, Other types of graphs that are important are the arc cos and the arc sine graphs. Now, I'm going to go through this really, really slowly here. Okay. So the arc sine, let me just start off with the arc sine graph. Arc sine is basically it's the inverse sine. Okay. So it's the inverse function of the sine graph. Now, if I look at the sine graph does not have a one-to-one mapping. Yeah. So therefore, if I just look at it as it does not have an inverse. But what I'm going to do instead is I'm going to restrict the domain. So I'm going to restrict the domain to make it one-to-one. I'm going to restrict it to pi over 2 minus pi over 2, 1 and minus 1. When you restrict it between that domain, you will get a restriction in your range as well. Now, how do you get the arc sine graph from that? What you do, as I said in the last sort of subsection, is you reflect it in the line y equals x. Okay. Now, when you reflect it in the line y equals x, you're going to get something that looks like this. Okay. So, not the best sketch I've ever done. You can find a better example in your textbook. But essentially, what happens is now the graph will go between the pink graph, which is the arc sine, has a maximum y value of pi over 2, which is 1.57, and a maximum value of minus pi over 2, which is minus 1.57. You'll also notice the domain of the pink graph is now going to be at 1 and then at minus 1 here. Okay. So essentially, the domain and range, they flip. That's another aspect of your function to inverse function. Okay, so here's the original function, here's the inverse function. The domain becomes the range becomes a domain. Okay, so you can see this. The original domain was between minus pi over 2 and pi over 2. That becomes the range of the inverse function. The range will be arc sine is between minus pi over 2 and pi over 2. The range of the original function was between 1 and minus 1. That becomes a domain of the inverse. And that makes sense. You can only arc sine values between minus 1 and 1. Okay, you can't go beyond that. Again, your textbook has the graphs on arc cos and arc tan. Arc tan not very likely to turn up, but nonetheless, it's there. So gone through a few of these things, how to get the inverse through sketching, arc sine, logs, equality law. Now, this is something that, you should know your laws of logs anyway, but it's something that's not really been explicitly told as an equality law. Essentially, if I've got something like this, on a log base A, x over y equals log base A, I don't know, 3. If two logs are the same, are equal to each other and their bases are equal, then we can deduce that the contents of those logs will be equal to each other. In essence, if two things are generally equal to each other, then we can say that log of that, of A equals log of B, regardless of the base. Okay. And actually, this goes both ways. If log of something equals log of something else, you can say the contents of those logs must be equal. Where's this coming useful? Sometimes I see students who just cross this out, and that's incorrect maths. That's not correct to cross out logs. You can't do that. Okay. So it's something that does come up in solving sometimes. Um, Another thing that I often see students struggling with is sigma notation. Sigma notation is definitely in your curriculum. So sigma notation, this is the symbol for sigma. It's the Greek symbol, it means sum. Okay. Whenever you see it, you just need to think about a couple of things. Where what it means is the context of sigma notation is around sequences and series. Okay, so within the sort of bracket of a sigma notation, you will have a sequence formula. Yeah, the number at the bottom of that sigma tells you the starting term. So you're going to sum a sequence with this formula from the first term, a number at the top, like it could be, for example, 10, up until the 10th term. And there are questions like this. And sometimes what you have to do is you have to generate a few numbers. And then if it's arithmetic or geometric, you make the right result. Yeah, if it's arithmetic, you've got your arithmetic sum formula, and you can use that. If it's geometric, you've got the geometric sum formula, and you can use that. Okay. And sometimes there are questions where it might not always have start from the first term. It might start, let's say, from the third term or any number at the bottom. And you need to start thinking a little bit more around this. Like, okay, if they want the sum from the third term till the 10th, then okay, so first term, second term, third term till the 10th term. The formulas that you see on the right-hand side, if it's arithmetic geometric, those formulas go from the first term up until that nth term, 10th term, whatever. They don't go from a third term. So you have to be a bit clever and go, okay, if I use my formula, I can get the sum from the first till the 10th. And then what I can do is I can find the sum of the first two and then take that away to get the sum between the third and the 10th. So just be aware of the sigma notation. It does come up. Right. So done all these. Recurrence relations, again, comes up in sequence series, and students often forget what it looks like. Okay. So recurrence relation is basically any equation that you see that has un plus one and some uh, function of un equals some function of un. Now, what does this all mean? Recurrence relations basically, what it does, it helps you to find the next term by using a function of the previous. Now, some sequences, they're kind of like direct sequences, like you have to add three to the previous term to get the next term. Some sort of sequences you have to use the previous term and input it in and get the next term. Some sequences don't have relationships with each other in that way. Some just something like this. That's a sequence. Okay, it's got periodicity to it, but there's no like you're not using the previous term to get the other one. So look out for this. How do you know you've got a recurrence relation when you've got a notation like this at the bottom, un plus one and un? Okay. And read the questions. They'll say to you the 10th term is equal to this, the ninth term is equal to that. And that's the sort of things that do come up really. Um, Next thing, I don't often see questions around this, cosec, sec, cot graphs. They don't really come up that often, but who's to say they won't come up in pure one or pure two across those two papers, okay? Pure paper one and pure paper two. So I would definitely go to the textbook and learn some basic principles around those graphs. What do they look like? What's the sort of domain or range of those graphs? About the next item on this list, which is the pure modeling worded questions. I want to keep that towards the end, actually. So another sort of thing that I think is quite useful for learners or students in the exam is understanding that integrals can be split up if there's this addition or subtraction in between. And I think that's really useful because it could simplify the work that you're doing. Okay. So, for example, if I've got, I don't know, something like this, a partial fraction problem. Yeah. I don't know, I'm just making this up. Yeah, then you can split that integral into three separate ones. Okay. And I would highly advise that you do that because that helps to focus what you're doing. Okay. So I can do that 1 over x minus 1 dx minus 3 over 3x plus 1 dx plus 3 over x plus 1 squared dx. Okay. And if you've got numbers, the numbers here are fairly okay to deal with, but sometimes you might have some numbers on the top of your integral sign or around your integrals question. Take them out. If I, let's say, had half e to the x plus, I don't know, half uh, sine x or something like that to integrate, take out the half from everything. Yeah. Factorize it out, whatever you need to. Just make life easier for yourself. Okay. When it comes to integration questions like this. Small angle approximation for cos. Now, the cos x small angle approximation looks like this: 1 minus x squared over 2. But some students forget that actually you won't always just get cos of x. You should treat it as cos of all of x squared. There's like a hidden bracket there almost. So if you've got, let's say, something not 1x, then that formula has to be adapted to this. Okay. So if you got, let's say, for example, you got cos 2x, the small angle approximation for that is 1 minus 2x all squared over 2. And you could simplify that. Last thing on this list before, penultimate thing actually, before I do the pure modeling worded questions is fractions within fractions. I have seen many students really struggle with questions which involve fractions within fractions. And it doesn't actually, it's not a topic within itself, but it's stuff that you have to be able to work through. And it can come up in trig proof, it can come up in range and domain, all those sorts of problems. What I mean is something like this. So let's say I've got two functions. I've got this here, and I've got g of x is this. Yeah. And I say to you, can you find the composite fgx? So you're putting g of x into there, and they might want it in a particular form. Well, okay, you put 1 over x in for that, you put 1 over x in for that. Now you might think, Ash, that's the end of the answer. No, the question might say, can you put it into a simplified form? Okay, so you've got fractions within a fraction. So I would take the numerator. Okay, right. How could I rewrite that into a fraction with a common denominator? Well, I would do 1 over x, GCSE maths here, fractions. How do you get that second fraction? You do x over x. So that's what the numerator becomes. Denominator is basically the same thing there. I mean, this is a fairly okay-ish example. You get 1 minus x over x. So you've got your numerator, you've got your denominator, and then you have to put them on top of each other. There's your numerator, there's a denominator, and I see some students freeze here as well. Remember, how do we divide fractions? You keep the first fraction, the numerator as it is. You are essentially dividing by the second fraction, aren't you? So remember GCSE, keep, fit, multiply. We're going to do the same thing here. We're going to keep first fraction, we're going to multiply by the flipped version of the second fraction. What you notice is the x's cancel out. We'll get 1 plus x over 1 minus x. Okay, so be aware of algebraic fractions that could turn a bit ugly like that. And just stay calm and just think, okay, how can I deal with the numerator? How can I deal with the denominator? And how can I do a keep, flip, multiply to simplify things as much as possible? Okay, so that's the end of this segment. I'm going to talk about mathematical modeling in the next. Right, this is the final segment of this video. I'm going to talk about the language around modeling questions. There are many types of modeling questions that could come up in your exam. You could have straight line modeling, quadratic modeling, exponential modeling, trig modeling. Differential equations can obviously link up with that as well. There are so many different types of modeling questions that could come up. It's really important there to really understand how can you answer those questions to like the part C. What's the limitation? Can you evaluate? Can you validate? what do you interpret this? And they're sort of worded 1 or 2 mark questions. So let's say in your exam in paper 1 or paper 2, or even paper 3, because mechanics, statistics, things could happen there as well. If they ask a question around state a limitation of the model, invariably students just freeze. They think, what's that mean, state a limitation of the model? Well, the secret meaning is, why will this formula eventually fail? And start thinking about what kind of extreme values will this function or formula fail for. Now, if it's a quadratic model, if it's a negative quadratic, there might be values on the x-axis, which when you plug it in will give you negative y values. Is that appropriate for a model? Let's say if you're thinking about the cost of a toy and you can model it as a quadratic model from a factory. I don't know. Then just think about that. Start looking for those extreme values. What happens when t becomes really big or t becomes really small? So an example answer could be, as t approaches infinity or as it gets really, really big, the population reaches infinity. So it could be like a population model. Now, this might not be possible. So stating limitations, questions like that, think about, where will this formula fail? Questions around evaluating or validating. Remember, models are an approximation to a real life problem. So often in A-level maths questions, you will get a model, you might be asked to put a value into it to get an output, and then you might be asked to compare against the real world value. So that's where your evaluation comes from. Like, does the maths from your model output, is it quite close to your real world value? And do a comparison. Okay, is it really far off? Is it really close? So that's evaluation. How far is that model away from reality? Um, Interpreting constants, that comes up quite a lot. Interpreting constants like a capital A or B. So start thinking about, okay, how could I get that capital A on its own? How can I get that B? What does that B represent? So start thinking, okay, if it's like a x to the power of something, then that a is normally the initial physical state. It's normally the value of the model when t is 0. Okay. Other sort of constants that you might be asked, you've got to think, okay, if this is a line equation, I've got y equals a plus bx. B is the gradient, clearly. So gradient is essentially this per unit x cross how much you're going up in the y. So interpreting constants can come in there. And then suggesting refinements. So this is the one that really, really students struggle with. Can you suggest a refinement? Essentially, how can you make the model more realistic? And some of the students really, they're quite generic answers, but you have to keep it specific to the problem. If you've got a question around a rugby ball being thrown, then suggest a refinement to the model might be account for air resistance, okay, in that model. If you've got something else happening, then you've got to look at the context and think, okay, how can I make that model more realistic? Now, obviously, these sort of part C, Ds of these modeling questions, they're not worth a lot of marks, but um, they all add up to be sort of get you over to the next grade boundary. Anyway, thank you for watching this video. It's made of 3 different segments, and I'll see if I can make any more if more ideas come to mind ahead of paper 2. But yeah, hopefully anything from this video will give you a little bit of an advantage in that paper.